Welcome to The Explainer. Today, we're looking at how artificial intelligence is totally shaking up one of the world's oldest and most important jobs, civil engineering. Yeah, from the bridges we cross every day to the buildings we live in, AI is really changing the game of how we build our world. You know, the challenges facing modern engineering are just huge. We're dealing with insane complexity, mountains of data, and safety standards that you just can't compromise on. And frankly, the old ways of doing things, relying on manual checks and just human intuition, they're starting to crack under the pressure. The solution isn't just to throw more people at the problem. It's about building smarter systems. And look, we're not just talking about creating faster calculators here. We're talking about building AI agents that can actually perceive their environment, reason with logic and probability, and then act rationally to hit their engineering goals. So today, we're going to open up this powerful toolkit that transforms real-world engineering headaches into computational models an AI can actually solve. All right, let's break down how this really works, starting with the biggest hurdle for pretty much any engineer, the rulebook. Okay, first up, let's talk about that universal engineering problem, trying to navigate a literal mountain of regulations and design rules. This is where we stop just reading the manual and start teaching the manual to the machine. So, picture this. You're designing a brand new skyscraper. You have to make sure every single beam, every window, every fire exit follows thousands of pages of safety and building codes. I mean, trying to do that by hand isn't just slow. A single mistake, one little oversight, could have absolutely massive consequences. So how do we get a computer to do this? Well, instead of having the AI try to read plain English, we use a special formal language called Propositional Logic. You can think of it like a super simple, ultra-strict grammar for computers, where any statement is either true or it's false, with no gray area. We literally translate a rule like, if a wall is a load-bearing wall, then it must be made of reinforced concrete, into a logical sentence the AI can process instantly, without any confusion. Just like that, a human rule becomes a machine-readable fact. And this whole process, it has a name. It's called knowledge engineering. It's how you turn a massive library of rules into a genuinely smart assistant. The AI gets its knowledge base, and then through a process called inference, it can start connecting the dots all on its own. It'll scan a building plan and instantly flag any part that doesn't follow the rules, making sure absolutely nothing gets missed. Okay, so our AI can follow the rules. That's a huge step, right? But what about making the best choice? How do we find the most efficient way to get something done, whether we're talking about moving materials around a site or figuring out where to build a new highway? These are the classic optimization problems that civil engineers deal with every single day. The number of possible routes for a fleet of trucks, or all the potential locations for a new hospital. It can be absolutely astronomical. Trying out every single possibility is just not an option. And this brings us to a really important idea. The difference between searching blindly and searching intelligently. So an uninformed search is kind of like trying to solve a maze by just trying every single path one by one. Sure, you'll get there eventually, but it's incredibly slow. But an informed search using an algorithm like A* has a secret weapon. It's called a heuristic. And you can think of a heuristic as just a smart rule of thumb, an educated guess. It's like having a compass that's always pointing you in the general direction of the exit. And this is where you see the real-world power. For moving materials on a big construction project, an informed AI doesn't just find a path from point A to point B, it finds the best path by factoring in things like traffic, the slope of the road, and fuel costs to save as much time and money as possible. That is the power of smart optimization. All right, but following rules and finding the best path is one thing. What happens when the real world decides to throw a curveball? Projects get delayed, materials might fail, the weather turns bad. We need AI that can handle uncertainty and actually plan for the unknown. We can't know for 100% sure if it's going to pour rain next Tuesday. But what we can do is calculate the probability of it happening and then model what that's likely to do to our construction schedule. We need a way to think in probabilities, not just in certainties. And that's where a fantastic tool called a Bayesian network comes in. The easiest way to think of it is as a map of cause and effect, but with probabilities attached to everything. Each little spot on the map or node is a variable, like rain or project delay. An arrow from rain to delay just shows that rain has an influence on the chances of a delay. This lets us ask really important questions like, okay, given that heavy rain is in the forecast, What is the new probability that we'll finish this project on time? Now, let's think about a different kind of uncertainty. The real structural health of a bridge is what we call a hidden state. We can't actually see the stress on the internal steel beams directly, right? But what we can do is observe evidence from sensors that measure things like vibration or strain. This is the perfect job for something called a hidden Markov model. It is a really clever way for an AI to work backwards. It takes all the data it can see, that sequence of sensor readings, and uses it to figure out the most likely story of what's happening that it can't see. It can tell us, hey, based on these vibrations, it's highly probable the bridge's internal state has shifted from stable to stressed. And this is a total game changer because it lets engineers go from making reactive repairs to doing proactive, predictive maintenance. Now, this is where it gets really cool. When we combine all these ideas, logic, search, and probability, we get to one of the most powerful and, honestly, most visible uses of AI in civil engineering today, giving machines the eyes of an expert inspector. I mean, just think about the sheer scale of our infrastructure. Having teams of people visually check every single inch of a bridge or a highway is a monumental task. It's incredibly time-consuming, it's expensive, and it can put inspectors in really dangerous situations. We need a whole new level of efficiency and accuracy. So how do we do it? Well, the solution is to give machines the ability to see and understand the world like an engineer does. We use a type of machine learning called supervised learning. It's a lot like showing a kid flashcards. We show a neural network thousands of pictures of concrete, and for each one we tell it, this is a crack, and this is not a crack. And over time, after seeing enough examples, the AI learns to recognize the visual patterns of defects all by itself. What's so fascinating here is that through this process, the computer starts to develop its own kind of visual intuition. By looking at massive amounts of data, the neural network just learns what a crack looks like in all kinds of different conditions. So now you can have drones with cameras become its eyes, flying along a bridge, feeding video to the AI, which then automatically flags any potential issues for a human expert to go and review. It focuses their attention exactly where it's needed most. So, what does this all add up to? When we put all these amazing tools together, what does the future of civil engineering actually look like? This whole journey, it's really about a fundamental shift in thinking. We're moving away from these uninformed brute force methods and toward informed, intelligent systems. We go from fixing things after they break to predicting when they might fail. And it's important to remember, AI isn't here to replace engineers. It's here to act as a powerful partner, to augment their skills so they can focus on the big picture design and decision-making. This chart really brings it all home. You can see a super clear pattern here. For every major challenge in civil engineering, there's a corresponding AI tool ready to help solve it. We've gone from using knowledge agents for the paperwork side of things, like compliance, all the way to using neural networks for the physical inspection of our infrastructure. This right here is the modern engineer's toolkit. It even includes things like natural language processing to make sense of the huge piles of text and project reports. And that really is the core idea. We're not just running algorithms anymore, we are building intelligent agents. By translating the physical constraints and the real-world challenges we face into computational problems, we can build smarter, safer, and much more efficient infrastructure for everybody. The tools are here. The frameworks for logic, for optimization, for learning, they are more accessible than they have ever been. So the only real limit now is the problems we choose to apply them to. The question is, what are we going to build next?